For this lecture video, I'm going to talk about the coefficient of variation, and I'm also going to talk about Chebyshev's theorem. These two topics are covered in the lecture on measures of variation, but they can be somewhat difficult, especially Chebyshev's theorem. Let me start with something that's a little bit easier to understand, which is the coefficient of variation. It is a measurement that is used to compare the variability of two different data sets whose units are different. I have the formula for coefficient of variation for a sample versus a population, or a statistic for that matter versus a parameter. It's the standard deviation divided by the mean times 100%. I'm going to deal primarily with a sample, since in this chapter, assume you're working with a sample unless you're told otherwise. If you are indeed dealing with a population, it would be population standard deviation sigma over population mean mu times 100%. Let's go back to the sample coefficient of variation formula. Again, coefficient of variation allows us to compare the variability of two different data sets whose units are different. Here's an example. The average score on an English final exam was 85 with a standard deviation of 5. The average score on a history final exam was 110 with a standard deviation of 8. Now, English and history are separate classes. It's not like I'm comparing two different English classes or two history classes. I'm comparing English and history and which class is more variable in terms of scores on the final exam. For English final exam, the average was an 85 with a standard deviation of 5. So that's 5 divided by 85, and if you change that to a percentage by multiplying by 100, it's about 5.9%. For history, the average score for history was 110 with a standard deviation of 8. So 8 divided by 110 changed to a percentage is 7.3. Since history has the larger coefficient of variation, the history scores on their final exam is more variable than the scores in the English class on their particular final exam. So based upon just knowing the mean of a data set and the standard deviation of a data set, we can find the coefficient of variation to compare two completely different data sets and be able to say which data set is more variable. We can calculate the coefficient of variation. To answer which data set is more variable, you would go with the larger coefficient of variation. History, more variable. English, less variable. When I say more variable, these are talking about the history exam scores within the history class. And whatever their class average happens to be, those history exam scores are more variable with respect to their class average than the English class, their scores with respect to the English class average. So more variability with their scores about their average, less variability with their scores about their average. Now, we don't know the individual scores of the English students. We don't even know how many students are in that class. We don't know the individual scores of the history students. And we don't know how many students are in that class. But we can still compare their variability by taking the coefficient of variation. More variability with their scores with respect to their class average in history, less variability with their scores with respect to their class average in English. And that's basically it when it comes to coefficient of variation. The next topic, and that's the standard question, by the way, for coefficient of variation. It's not much more complicated than that. The next topic is Chebyshev's theorem. It applies to any data set that you can imagine. It's a very general theorem. As a matter of fact, I often tell students to write down their own data set, and I could actually help the student prove that Chebyshev theorem applies to their data set that they created. So every data set everywhere is very general. Chebyshev is a famous mathematician that found out the following theorem is always true. He discovered that the proportion of data values in a data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k has to be strictly above 1. K represents the number of standard deviations above or below the mean. Now that's a very vague theorem, but I'm going to give you some details that will hopefully explain what Chebyshev is saying in his theorem. First of all, 1 minus 1 over k squared I call Chebyshev's formula. And the three important k values that you want to have memorized, when k is 2 standard deviations above or below the mean and you plug it into this formula, you get the decimal 0.75 or the percentage 75%. So let's read this. Chebyshev discovered that the proportion of data values from any given data set that will fall within 2 standard deviations of the mean of that data set will be at least 75%. So 75% of the data values in the data set are guaranteed to fall within 2 standard deviations of the mean. And that represents 2 standard deviations below the mean and 2 standard deviations above the mean. When k is 3 and it's plugged into its formula and you change the fraction to a decimal into a percentage, it's approximately 89%. Chebyshev discovered that the proportion of data values from a data set that will fall within 3 standard deviations of the mean will be at least 89%. So 89% of all the data values in a given data set are guaranteed to fall within 3 standard deviations of the mean of the data set, 3 below and 3 above. And then famously, when k is 4 and you plug it into its formula and change the fraction to a decimal to a percentage, you get 94% of all data values in a data set will fall within 4 standard deviations of the mean. And this would represent 4 standard deviations below and 4 standard deviations above. So this is his very, very general theorem. 2 standard deviations, 3 standard deviations, and k is 4 standard deviations. Now k doesn't have to be just 2, 3, and 4. These are just the special k's, kind of like the cereal, the special k cereal that you have to memorize and their corresponding percentages. K has to be greater than 1. That's the only restriction. So we can talk about 1.5 standard deviations above and below the mean. We can talk about 2.5 standard deviations above and below the mean, or 3.5 standard deviations above and below the mean. Plug it into his formula and you would be guaranteed that percentage. So, going to the next page, you have a visual of what Chebyshev is talking about. This is representing a data set, and every data set has a mean and a standard deviation. These increments here, and they're supposed to be equal increments, represent 1 standard deviation above and 1 standard deviation below. So x bar plus s, x bar minus s, and then x bar plus 2 times s, x bar plus 3, x bar plus 4 times s, and then I go the opposite direction, x bar minus s, x bar minus 2s, minus 3s, minus 4s. Within 2 standard deviations of the mean, that would be these two numbers, 75% of the data values in a data set are guaranteed, at least 75% are guaranteed to fall there. Within 3 standard deviations of the mean, at least 89% of the data values are guaranteed to fall there. And within 4 standard deviations of the mean, at least 94% of the data values are expected to fall there. As k gets larger, which is the number of standard deviations above and below the mean, you can see that the percentages are increasing each time. So as k gets larger, the percentages get larger, and we're including more and more data that's coming from the data set. Here's a great example, because examples tell you so much more than just a general graph. Let's take the grades of 6 students, 80, 61, 85, 50, 79, and 25. 25 is a pretty low grade. And I want to prove that at least 75% of all the scores fall within 2 standard deviations of the mean. That's what Chebyshev promises. He also promises at least 89% will fall within 3 standard deviations of the mean, and 94% will fall within 4 standard deviations of the mean. I just want to work on the 2 standard deviations. To do that and prove that, I will have to know the class average and I will have to know the class standard deviation. All I did is I took the time, and I did not even do this by hand, I took the time to put the values into my calculator, stat, and I'm going to go ahead and just use the L2 column, 80, 61, 85, 50, 79, and 25. And let the calculator do the magic for me. I'm going to go to Stat, Calculate, One Variable Statistics, and I'm going to say my data is raw data. It's in my L2, so you can use something other than just L1 if it's a raw data problem. I want to put it in L2 and press Calculate. And it looks like the average is 63.3 repeating, and the standard deviation is 23.00144,923. So you have to know those values before you can prove Chebyshev's theorem. And I wrote those 2 values down, and I rounded to the nearest tenth because my raw data values are whole numbers. So round to an additional decimal place. Now, with those 2 numbers, I could literally come up here and fill in every single number. X bar is 63.3 and S is about a 23. So all of these numbers could be filled in, and I would actually know these numbers on the axis. For 2 standard deviations, below and above, I'm talking about X bar minus 2S and X bar plus 2S. Those numbers on the axis above, if I plug in, 2 standard deviations below is a grade of 17.3, and 2 standard deviations above the class average is 109.3. And those are the 2 values that would fall on the axis here up above in place of these 2 formulas. 17.3 to 109.3. Chebyshev says that at least 75% of all the scores in this class will fall within 2 standard deviations of the mean. So between 17.3 and 109.3. And that's easy enough to prove. All you have to do go back to your data set. These are the 6 students and their scores, and which data values fall within 2 standard deviations of the mean. Again, these are the values. I put check marks above the values that fall between 17.3 and 109.3. All 6 students fall there. That's 100%. But remember, Chebyshev guarantees at least 75%. All of those mean at least 75% will fall within 2 standard deviations of the mean. So it's okay that I got exactly 100% because Chebyshev promises 75% or more. It just so happens specifically it's 100% of the data values fall within 2 standard deviations of the mean. So that's a great example of Chebyshev's theorem with a specific example there. Here's another example. I have a data set, and again, for Chebyshev to make sense, you need the average and you need the standard deviation. I really should round this standard deviation to 6.1. For some reason in the example, I left it at 6.110, but the rounding rule says to round to an additional decimal place, so I should be utilizing just 6.1. So just make note of that. And N is 10. So I have 10 pieces of data. These could be test scores. I don't know. They could be anything, but it is a data set with an average of 39 and a standard deviation of 6.110. It says determine what % of data values fall within 1.15 standard deviations of the mean. So that's not one of the standard deviations that we have memorized for Chebyshev. But if we plug 1.15 into his formula, we'll see what Chebyshev promises with 1.15. 1 minus parentheses 1 divided by 1.15 squared. That is Chebyshev's formula of 1 minus 1 divided by k squared. 1.15 is the number of standard deviations below, and 1.15 is the number of standard deviations above. This is his formula, and it gives you the promised percentage. Multiply by 100, and I'm going to say that he promises about, I would say approximately at least 24% of the data values in a data set, no matter what the data set, at least 24% of the data values in any given data set will fall within 1.15 standard deviations from the mean, according to his formula, where k is 1.15 standard deviations. So 1 minus 1 divided by k squared gives us at least 24%. That's what he promises, 24% or more. So with this specific example, what I did is I went ahead and calculated the numbers that represent 1.15 standard deviations below and 1.15 standard deviations above. The average is 39. The standard deviation, I did use a 6.110. I plugged it in, and I got 31.9735 and 46.0265. I go to the actual data set and I put check marks above the values that fall within 1.15 standard deviations of the mean. And it looks like out of the 10 values that I have, 8 of them fall in that range. 80% of these data values in this data set are found to fall within 1.15 standard deviations from the mean. 1.15 standard deviations below, which is this number, 1.15 standard deviations above, which is this number, and 80% of the values fall within that range, 1.15 standard deviations. Chebyshev, by his formula, promises at least 24%. So his theorem, again, holds true, 24% or more. In general, 24% is promised, but specifically is 80%. Be careful on a test. I could ask you this question, and I could say, according to Chebyshev's theorem, what percentage is promised? And for 1.15 standard deviations, you would have to use this formula and tell me at least 24% of the values are promised to fall there. Then I could give you the same problem, and it looked just like this. Determine the actual percentage of data values that fall within 1.15 standard deviations of the mean. And you'd have to calculate that range and physically see how many fall there, 8 out of 10 or 80%. So there's a difference in the general percentage Chebyshev promises, at least 24%, and the specific percentage that we find, which is 80%. Be very, very careful with how I ask the question. So, the last thing I want to talk about in regards to Chebyshev, and I am going to give another example, is this particular type of situation you'll have to cover. And you'll see this type of question a lot. It says, suppose that a given data set has a mean of 80 and a standard deviation of 10. At least, what percentage of values will fall between 60 and 100? So if you notice, I'm not given the data in the data set. I'm not even given the size of the data set, but I know the average is 80 and the standard deviation is 10. Just with those two numbers alone, I can tell you the percentage of the data values that will fall between 60 and 100. I don't know the data values. I don't know the size of the data set. But with these values, and according to Chebyshev, I can give you the percentage of values that fall within 60 and 100. These are the steps. Take your larger value and subtract your mean of 80, and you get a difference of 20. Just so happens that the difference between the smaller value and the mean of 80 is a positive difference of 20. So the difference between 180 is 20. The difference between 60 and 80 is 20. But I say in the step, take your larger value of 100 and subtract the mean. That positive difference is 20. K, which represents the number of standard deviations above and below, is going to be this positive difference divided by S, which is 10. So 20 divided by 10 is 2. K is 2 standard deviations. We've memorized this one. When you put 2 into Chebyshev's formula, 75%. So 75% of all the data values in this data set, if we knew this actual data set and these actual data values, we would be able to show that at least 75% of them fall within 2 standard deviations of the mean, and it just so happens that 60 and 100 represent the 2 standard deviations from the mean. And I can show you that. That's actually not given here, but I can draw that picture for you. These are the steps, but if you need a visual for this same problem, you could always do this. X bar is 80, X bar plus S, X bar plus 2S, X bar plus 3S, X bar minus S, X bar minus 2S, X bar minus 3S. And I just add S each time, which is 10. So 80 plus the 10 is 90. 80 plus 2 times 10 is 100. 80 plus 3 times 10 is 110. Or you just add 10 each time. 80 plus 10 plus 10 plus 10. 80 minus 1 standard deviation is 70. 80 minus 2 standard deviations is 60. And 80 minus 3 standard deviations is 50. So I can fill in this whole axis here just by knowing my mean is 80 and my standard deviation is 10. What represents 2 standard deviations from the mean? If you actually fill in those numbers, it's 60 and 100. So Chebyshev promises that at least 75% of all the data values in the data set will fall within 60 and 100. You do not have to draw this graph to answer this type of question. All you have to do is follow the steps. Because at the very beginning, if you don't draw this graph, you're not necessarily going to see, hey, 60 falls at 2 standard deviations below, and 100 falls at 2 standard deviations above, without the graph. You're not going to see that. You'll have to go through the steps to find that K is 2, so that you know your percentage promised by Chebyshev. So I recommend, even though you may want to draw out the visual for it, the steps are the best way to approach that type of problem. And those steps will get you that percentage every time. It always ends up with step number 3, using his formula. So you want to work on finding K, and once you find K, you use this formula to find the guaranteed percentage, so at least 75%. The only other thing I want to show you really quickly is the empirical rule. The empirical rule is kind of like Chebyshev, but it doesn't apply to every data set everywhere. It only applies to data sets that when you graph them, their graph is said to be normal, bell-shaped, symmetrical. These are those histograms that are symmetrical. The mean equals the median equals the mode and located at the center of the distribution. We're going to talk about these in the next chapter, which is chapter 5 in your Pearson textbook. And we're going to talk about normal distributions and how they satisfy the empirical rule. And all you have to know for now is just with the empirical rule, it's more specific than Chebyshev. It's not going to apply to every data set. It's only going to apply to a symmetrical, bell-shaped, normal data set. Chebyshev applies to every data set with its guaranteed percentages. These are the 3 percentages guaranteed in the empirical rule. If you have a data set, approximately 68% of the data values will fall within 1 standard deviation of the mean. Approximately 95% of the data values will fall within 2 standard deviations of the mean, and approximately 99.7% of the data values will fall within 3 standard deviations. And this talks about 1 above, 1 below, 2 above, 2 below, 3 above, 3 below standard deviations. And those are the guaranteed percentages when it's a normal distribution, and that's the empirical rule. Way different from Chebyshev. Excuse me. And you'll see that in the next section. So, I have another example before I stop the video of Chebyshev. This is a specific example, and we covered this example in the last lecture on measures of variation, 8 students and their grades, and answer these questions involving Chebyshev's theorem. And if you remember from the last video, we found that the sample mean was 81.6, and we found the sample standard deviation was 11.8. So we found this specifically the long way using the formula for sample standard deviation. Now I want to talk about Chebyshev using this same example. The first thing I did, though, is I did graph the individual scores for the students with respect to the class average of 81.6. I incremented in terms of 10, 60, 70, 80, 90, 100, and the dot plot is represented. So this is the person with the 65. These two people are the students with the 72. One student made an 80. Two students made an 85. One student made a 94, and one student made a grade of 100. So you can see the spread of the data in the data set with respect to the average of 81.6. And it's not a very large standard deviation again, but it's not very small either. I do have some extreme cases of 65 and 100. The question here, though, is find the range in which at least 75%, 89%, and 94% of the values will fall according to Chebyshev. So I'll do that here. I wrote an axis with x bar plus s, x bar plus 2s, x bar plus 3s, and x bar plus 4s. I did the same thing on the other side. Minus 1, minus 2, minus 3, minus 4. And I filled in, I found those numbers using my mean of 81.6 and my standard deviation of 11.8. I found those numbers. Another thing you could do easily on the calculator, which would help you fill in these numbers very quickly, is this. 81.6 plus 11.8 is one standard deviation above, plus 11.8, two standard deviations above, plus 11.8, three standard deviations above, plus 128, got a little ahead of myself, plus 11.8 is 128.8. You can go in the other direction, 81.6 minus 11.8, there's one standard deviation below, minus 11.8, two standard deviations below, minus 11.8, three standard deviations below, and minus 11.8, four standard deviations below. So very easy to fill in the graph using the calculator, and then that answers your question. Find the range in which at least 75% of the scores are guaranteed to fall. Find the range in which at least 89% of the scores are guaranteed to fall. And find the range in which at least 94% of the scores are guaranteed to fall. And these would be the ranges for these specific percentages there, according to Chebyshev's theorem. I could also ask you to find the range in which at least, I guess I would say, let me say this. Let's say that we're talking about 1.5 standard deviations above and below. What would those numbers be on the axis? And then we'll talk about the guaranteed percentage by Chebyshev. If you put in K to be 1.5, that's 81.6 minus 1.5 times 11.8, and you get 63.9. And then 1.5 standard deviations above, 81.6 plus 1.5 times 11.8 is 99.3. So I'm going to come up here. This is 1.5 standard deviations below, and this represents 1.5 standard deviations above. So x bar plus 1.5s, and then this is x bar minus 1.5s. Those numbers are 63.9 and 99.3. And when you look at the visual, how the numbers increase from left to right, negative infinity to positive infinity, 34.4, 46.2, 58, 63.9, 69.8, 81.6, 43.4, 99.3, 105.2. So these values, 63.9 and 99.3, at least what percentage of values are guaranteed to fall between 99.3 and 63.9 and 99.3. To find the percentage, all you have to do is plug 1.15 into Chebyshev's formula. And I'll show you that on the calculator. 1 minus parentheses, 1 divided by 1.5 squared, closed in parentheses. Multiply by 100, and that's 56% of the values are guaranteed to fall within 1.5 standard deviations of the mean. And that should make sense also. 1.5, 2, 3, and 4, the percentages are increasing each time. So Chebyshev promises at least 56% of all the data values in the data set will fall within 1.5 standard deviations of the mean. The 63.9 is 1.5 standard deviations below, and the 99.3 is 1.5 standard deviations above. Then I can ask you specifically, how many values in this data set fall within 1.5 standard deviations of the mean? Chebyshev promises 56%, but specifically speaking, how many of the values fall there? So let's do that. To do that, I'll write out the data values again for the data set. 65, 72, 72, 80, 85, 85, 94, and 100. Here. And again, we know the average is 81.6 approximately, and the standard deviation is about 11.8. We just found that when K is 1.5, Chebyshev promises at least 56% will fall within 1.5 standard deviations of the mean. And we found those numbers by plugging in 1.5 standard deviations below, 1.5 standard deviations above, and I'll do that here again. 81.6 minus 1.5 times 11.8 is the 63.9, and then 81.6 plus 1.5 times 11.8 is the 99.3. And I'm going to go to my data set and put check marks above those values that fall in that range. 65, yes. 72, yes. 72, yes. 80, yes. 85, 85. 94, yes. 100 does not. It's too large. So the 65 would be included because it goes from 63.9 to 99.3. And all the values through 94 would be included, but the 100 is outside of the range. That is going to be in this set of 1, 2, 3, 4, 5, 6, 7, 8 values. 7 out of 8 of them fall within 1.5 standard deviations of the mean. And that gives a decimal point 875. Which is 87.5% specifically. Again, on the test, I could give you a data set like this, and I could say, according to Chebyshev's theorem, what is the general percentage promise to fall, or for what's the general percentage promised? So, with 1.5 standard deviations, at least 56% of the values are guaranteed to fall within 1.5 standard deviations, at least 56%. So I could ask you the general percentage guaranteed by Chebyshev's theorem, but then I can turn around and say, okay, since you do know the data set and you know the individual values and you know the mean and standard deviation, obviously, what is the specific percentage that falls within 1.5 standard deviations of the mean? And it's as easy as going up and counting how many fall in that actual range. 7 out of 8, or 87.5. Chebyshev holds true because he says at least 56%, 56% or more. It just so happens that it's exactly 87.5% that falls within 1.5 standard deviations of the mean. So know the general percentage and be able to find the specific percentage for Chebyshev's theorem. And that concludes Chebyshev's theorem. I hope that you understand Chebyshev's theorem. I did not have the time that I needed to cover it in class, so I wanted to make a video, and I hope